To detect a single photon, you have to solve a massive scale problem, translating one minuscule quantum energy event into a readable, macroscopic electrical current. Standard optical sensors cannot operate at this scale. The inherent electrical noise inside a conventional sensor easily overpowers and obscures the tiny signal generated by a single photon. Capturing that signal requires specialized hardware designed specifically for this extreme environment, the Single Photon Avalanche Diode, or SPAD. This device relies on Geiger mode, an operational state named for its similarity to how a Geiger counter registers radiation. Detecting a solitary photon requires intentionally pushing a semiconductor into a highly unstable state known as reverse breakdown. By forcing this quantum event to trigger a massive electrical reaction, we can detect the photon without destroying the diode. In professional engineering circles, SPADs are often conflated with standard avalanche photodiodes, or APDs. They are frequently treated as the same class of device, but their operational limits are distinct. The absolute threshold dividing these two technologies is the breakdown voltage, denoted as VB. An APD operates below the breakdown voltage threshold, producing a linear, finite gain. It lacks the strength to time a single photon. A SPAD operates well above the breakdown threshold. Crossing that line makes the gain effectively infinite. Operating in this overbiased Geiger mode generates exceptionally high electric fields deep inside the semiconductor material. Crossing the breakdown voltage threshold represents a binary shift from linear amplification to a self-sustaining switch. We map the internal architecture allowing the device to survive Geiger mode using this cross-sectional SPAD diagram. Incident radiation enters the top active region. Below sits the N+ region, with a thick p-type substrate base. Sandwiched between them is the critical depletion region. Because the overall device is reverse biased above VB, the intense electric field concentrates entirely within this specific depletion layer. The physical layout of the PN junction acts as a specialized pressure chamber, confining massive electrical potential energy squarely inside the depletion zone. When an incident photon penetrates the active region, it injects a primary charge carrier into the depletion layer. The extreme electric field accelerates it violently, driving impact ionization. The carrier smashes into lattice atoms, knocking loose secondary charge carriers. These secondary carriers are immediately grabbed by the electric field, striking more atoms and setting off a chain reaction. This creates an exponential, self-sustaining avalanche of charge carriers that rapidly fills the entire depletion layer. This microscopic physics results in a macroscopic steady current, typically in the milliampere range. Geiger mode creates a controlled, localized lightning strike, where one quantum drop initiates an electrical flood that conventional hardware can easily read. While the volume of the current is important, the sheer speed of the avalanche is what makes this technology valuable. On a time domain graph, the avalanche current reaches its peak in the sub-nanosecond scale. The leading edge of this sudden current pulse serves as a highly precise marker for the exact arrival time of the original photon. The ultra-low margin of error in this timing marker is known as picosecond time jitter. This extreme level of temporal precision is the absolute requirement for advanced timing-dependent technologies like LiDAR depth mapping and quantum cryptography. By generating this immediate response, the SPAD locks the photon's arrival to a rigid, picosecond accurate timeline. The self-sustaining nature of the avalanche presents an inherent operational challenge. Once triggered, the milliampere current flows continuously and will not stop on its own. While this current is flowing, the sensor is blind and incapable of detecting any subsequent photons. To reset the sensor, the system executes quenching, an intervention that forces the avalanche to cease. To stop the current, the bias voltage across the SPAD is actively lowered down to, or below, the breakdown voltage threshold. Lowering the voltage drops the electric field density inside the depletion layer. The weakened field can no longer accelerate carriers hard enough to maintain impact ionization. The multiplication process halts, and the current ceases entirely. To keep a SPAD functional, the system must actively suppress and kill the very avalanche it was designed to maximize. The final step is the reset. Bias voltage is forced back up. This restores the extreme electric field, rearming the trap for the next photon. The life cycle of a SPAD is a rapid, violent oscillation through 4 distinct phases: trigger, avalanche, quench, and reset. This cyclical, binary operation differs strictly from the steady, linear behavior of standard APDs, establishing the Geiger mode operational framework. The SPAD functions as an active, oscillating engine, wielding the high energy threshold of semiconductor physics to capture the smallest units of light in the universe.